Welcome to the Explainer. We're surrounded by things that just work. And today, we're going to pull back the curtain on the invisible rules that make it all possible. It's this secret language that lets every single screw, every gear, every tiny microchip fit together perfectly.
All right, let's just start with a feeling I think we've all had. You're trying to build something. Maybe it's that bookshelf you got on a flat box, and the parts just won't fit. The holes are a little off. A piece is just not quite right. It's so frustrating, right?
Okay, now take that frustration and imagine it on an industrial scale. We're talking about manufacturers making millions of parts, sometimes in totally different factories all over the globe. For them, it's not just an annoyance, it's this massive, massive challenge, and it needs a really smart solution.
Yeah, that's really the big question, isn't it? How can you be absolutely sure that a part made, say, in Germany is going to fit perfectly with another part made in Japan every single time? It's this huge problem of reliability and precision.
So the answer? It's not as simple as just making things the right size. No, the real answer is this kind of secret, symbolic language, one that goes way beyond just basic measurements. It's a language all about shape and how things are angled and their true form.
And this system has a name. It's called geometric dimensioning and tolerancing, or what everyone in the field calls it, GD&T. Think of it as a universal language for engineers, all governed by these big international standards. And what's so cool is that it doesn't just say how big something is. It tells you its exact shape, how it's oriented to everything else, and precisely where it's supposed to be.
Okay, so check this out. This slide really shows you the difference. A simple dimension, that's like just saying a word. But GD&T, that's like writing a whole perfectly clear sentence. There's no room for guessing. It doesn't just say, hey, the hole is 10 millimeters wide. It says, this hole is 10 millimeters wide, and it has to be this circular, and it has to be perfectly perpendicular to this surface, all within these incredibly tiny but acceptable ranges of error.
So, how does this whole language actually work in the real world? Well, it's actually a really logical three-step process. It's how you get from a simple drawing to a complex machine where everything just works.
Yeah, it really comes down to this simple cycle. First, you specify, then you measure, and finally, you analyze. That's it. That's the loop that takes a blueprint and turns it into a part you can count on. All right, step 1, specify. This is where designers lay down all the rules, right on the blueprint. They use this whole library of special symbols to define every single important feature. And, critically, they set up what's called a datum reference frame. You can think of it like a fixed starting point, a 0-0 coordinate, so that all the other measurements have a common, stable reference. It makes sure everyone's reading from the same playbook.
Okay, next up, measure. You've got the plan, now you have to check if the real part actually matches it. And to check these super tiny tolerances, engineers use some just incredible technology. We're talking about things like coordinate measuring machines, or CMMs, that can map out a part's surface with microscopic precision, or even X-ray machines that can literally see inside a part to check its guts without having to cut it open. It's amazing stuff.
And then, step 3, analyze. All that data gets crunched. And this is a really key point. It's not just about trying to be absolutely perfect. Perfection is expensive. It's about finding that sweet spot, that perfect balance of being good enough to work flawlessly, so the whole assembly is reliable, but without making the cost to produce it go through the roof.
And this whole language, it's not just for old-school factories with smokestacks. No way. It is absolutely essential for the high-tech stuff that's building our future.
Think about 3D printing, what the pros call additive manufacturing. When you're building up these super complex parts, layer by tiny layer, little errors can creep in. Is that surface truly flat? Is that tube perfectly round? GD&T gives you the tools to control those exact shapes, making sure these futuristic parts actually work.
And this is where things get really cool, kind of like science fiction. Companies are now making digital twins. These are perfect virtual models of real parts. It's like a virtual fitting room. They can take thousands of these digital parts, each with its own tiny acceptable imperfection, and simulate how they'll all fit together. This way they can figure out the best way to assemble everything before any real metal is even cut. It saves a ton of time and money.
And the stakes for getting this right can be just enormous. This quote here is talking about building fusion reactors. You've got these huge, massive segments of a vacuum chamber that have to line up almost perfectly. So whether we're talking about the phone in your pocket or these giant world-changing science projects, the precision of every single piece is absolutely non-negotiable.
So, okay, why should you care about any of this if you're not an engineer? Let's step back for a second and look at the big picture here.
Because this whole system, GD&T, it's like the invisible blueprint that literally holds our modern world together. The phone you're holding, the car you drive, the plane you fly in, every single complex machine that makes our lives work, they are all reliable and safe because of this hidden language, this language of precision.
And it's a system that's always being pushed to its limits, right? We're always demanding more and more control over the physical world, which leaves us with this really interesting question to think about. As our tech gets smaller and faster and even more complex, just how perfect can we actually make things? Is there an absolute limit to human precision?